All right, the last little thing that you need to understand is a concept called isomers. And isomers are listed here as organic molecules that have the same number of atoms, which means the same molecular formula, but of different molecular shapes, which means they'll also have a different organic name when we get into that section, and they will behave differently. So let's just keep going, and we'll talk more about isomers later on, but I just want to give you a general idea here. So as the number of carbon atoms increases, the number of potential isomers also increases. And this is why, this right here is why molecular formulas are very unuseful. And let me give you an example to go along with this. Let's switch over to another screen here. If I took the molecule that we were working with already, C5H12, that's its molecular formula. That molecule has 3 isomers. So you could have 3 completely different molecules that have the same 5 carbons and 12 H's. But they would each have a different name, they would each have different boiling points, different behaviors, different properties. The bigger we get, the higher that number is going to get. So if I take C6H14, now I have 5 potential isomers. If we jump a little bit to C10H22, that number goes up to 75 isomers. So saying C10H22 is pretty useless because that just means it's one of 75 different molecules that each are different from each other. And just to show you a real extreme example, C20H42, go ahead and take a guess just in your head. How many isomers do you think C20H42 would have? And the correct answer is 366,619 different isomers. So this is why molecular formulas are almost useless to us. They don't tell me anything. That C20H42 just means it could be one of 1/3 of a million different molecules that are a possibility. So that's why we don't really do a whole lot with molecular formulas. But you do need to understand a little bit about isomers. So let me clear this, and normally the last thing we would do in this lesson is model out some of these isomers to see how they look. But let me just see if I can do it for you on the screen here to show you at least the isomers for C5H12. So the simplest one would be to have 5 carbons in a row like this, and all of the H's. If we count this out, that's 5 carbons and my 12 H's that I needed. That would be the simplest isomer of C5H12. Now, I'm going to not draw in the H's this time. I'll draw the dashes, but not every single H, just to save time. But keep in mind that for a real structural diagram, you should be drawing in all of the H's. So there's the simplest one. The next one would be, what if I could break off this end hydrogen, or this end group right here? What if we broke that off and attached it somewhere else as a branch? So what if I have 4 carbons in a row, and then I attach that as a branch there, and then I fill everything up following the honk rule, and I still have C5H12. The last molecule that you could end up with is to break off another one, and you'd end up with this arrangement. Still C5H12, everything's there, but that's a different molecule than either of those other two, and it's going to have its own name and its own properties. Now, doing the actual isomers, don't worry about too much for right now. We'll go into that when we get into the next lesson. But just so you can see as an idea that these are 3 different arrangements of atoms that all have the same molecular formula. That's what an isomer is. Just make sure you understand that concept. And we will practice isomers for the different types of molecules, different types of organic molecules as we go along.